In episode 34, titled 3.2 Use Dispersion Measures, Variance and Standard Deviation to Gauge Spread, the emphasis shifts from finding a typical value to understanding how widely outcomes vary around that typical value. Averages are comforting because they give one clean number, but spread is what tells you whether that average represents a stable experience or a chaotic mix of good and bad cases. In many real business settings, two teams can share the same average performance, while one team delivers consistent results and the other swings wildly between excellent and terrible, and those are not the same operational reality. The practical goal is to treat spread as a decision signal, because spread often predicts risk, workload surprises, customer dissatisfaction, and the likelihood that a process will fail when pressure rises. Variance is a measure of spread defined as the average square distance of values from the mean, which sounds abstract until you connect it to what it is trying to do. The distance from the mean part captures how far each observation is from the average, but the squaring step matters because it prevents positive and negative deviations from canceling each other out. Squaring also emphasizes larger deviations, which aligns with many real-world concerns, since extreme delays and extreme costs usually matter more than small wobbles around the center. When you think of variance, it helps to hear it as how much variation exists with extra weight on big departures, because that is the behavior it encodes even before any formulas appear. The standard deviation, spoken as standard deviation on first mention, is the square root of variance, which returns the measure of spread back into the original units of the data. That single move makes interpretation far more intuitive because a variance in squared hours or squared dollars is not something people naturally reason about. With SD, the spread is expressed in hours, dollars, days, or whatever unit the metric uses, so it becomes possible to say that typical variation is roughly plus or minus some amount around the mean. This does not mean most values fall neatly inside one SD, but it does give a scale for how noisy the process is and how reliable the average will feel to real stakeholders. In practice, SD is often the better communication tool, while variance remains the underlying mathematical foundation. A larger spread generally signals less consistency in outcomes, which is often what leaders actually need to know when they ask whether performance is stable. Low spread means results cluster tightly around the mean, so the average is a decent stand-in for what most people experience most of the time. High spread means outcomes are scattered, so the average can be misleading because it blends fast cases and slow cases into a single number that no one actually experiences. This matters for service, security, and operations because consistency is often the difference between a process that can be trusted and a process that constantly needs escalation and exception handling. When you interpret spread, you are really asking whether the process behaves like a dependable machine or like a system that produces surprises. Comparing spreads across groups is one of the quickest ways to spot unstable processes, especially when the means look similar and therefore fail to highlight the problem. If one region has the same average delivery time as another, but a much larger SD, that region likely has bottlenecks, inconsistent staffing, unreliable handoffs, or uneven demand that causes frequent delays. If one channel shows a tight spread while another shows a wide spread, the widespread channel may have measurement issues, inconsistent customer behavior, or operational variability that deserves investigation. Spread comparisons also help avoid false celebrations because a mean can improve while spread worsens, leaving many customers with worse experiences even though the overall average looks better. This group lens turns dispersion measures into a practical diagnostic tool rather than a purely statistical concept. Spread connects directly to risk when planning inventory or staffing because variability is what breaks plans built on averages. Inventory planning based on average demand can fail when demand has high spread, leading to frequent stockouts and costly rush replenishment even if the average demand is accurately estimated. Staffing plans based on average workload can collapse during spikes, producing long wait times and burnout, again, even if the average workload is correct. In these settings, the mean tells you what happens in the long run, but spread tells you how often you will be in trouble in the short run. This is why mature planning often uses both center and spread, because reliability requires understanding the range of plausible outcomes, not just the typical one. A delivery time example grounds interpretation because it is easy to picture what customers feel when spread changes. Imagine two carriers with the same average delivery time of 3 days, but one has an SD of half a day while the other has an SD of 2 days. The first carrier produces a fairly predictable experience where most deliveries cluster near 3 days, while the second produces a mixed experience where many deliveries arrive much earlier or much later than 3 days, and the late deliveries drive complaints and support volume. The second carrier can still report the same average, but the business impact differs because uncertainty drives customer anxiety, refund requests, and operational escalation. In a story like this, spread becomes the real quality signal because predictability is often more valuable than a marginal change in average speed. Confusion between sample and population calculations is a common pitfall, and it matters because it changes how variance and SD are computed when you do not have every observation in the full population. A population calculation assumes the data includes all relevant cases, such as every delivery in the period, so the computed spread describes that complete group. A sample calculation assumes the data is a subset used to estimate the population, such as a sampled set of deliveries or a survey-based estimate of delivery experience, and the calculation adjusts to avoid systematically underestimating spread. The practical takeaway is not memorizing the adjustment, but knowing when you are summarizing a complete set versus estimating a larger set, because that determines how confident you should be in the spread estimate. On exam-style scenarios, recognizing sample versus population is often the key to selecting the right approach and describing uncertainty honestly. Outliers can inflate spread dramatically, which is both a feature and a risk, depending on whether those outliers represent real, rare events or measurement defects. If a small number of deliveries take 30 days due to a known disruption, the SD will rise sharply, and that may be exactly what you want because it reflects the operational risk customers faced during that period. If those extreme values come from a unit bug, a parsing error, or a duplicate record that multiplies a delay, then the inflated spread is a warning that data quality is driving the story rather than real performance. The disciplined move is to investigate outliers before explaining spread changes as process instability, because outliers can be a signal of genuine risk or a signal that the measurement broke. Either way, outliers deserve attention because they often carry the most business consequence. When distributions look skewed, pairing spread with the median helps keep interpretation grounded because mean-centered spread measures can feel distorted by long tails. In a right-skewed distribution, a small number of large values can pull the mean upward and inflate variance, while the median stays closer to what most cases look like. In that setting, describing the median as the typical case and using spread to describe uncertainty around performance can communicate reality more accurately than relying on the mean alone. This pairing is also helpful for explaining why a process feels worse even when the mean is stable, because customers tend to remember tail events, and tail events become visible through dispersion. The practical message is that spread is still valuable under skew, but the center you anchor to should match how the distribution behaves and how the audience experiences the outcome. Explaining spread in real-world terms often works best through ranges and implications because most stakeholders do not think naturally in square distances or even in abstract deviations. A clear explanation connects SD to what it means for typical variation, while also noting that real processes can produce outcomes beyond one SD, especially when distributions are not perfectly normal. You might describe a delivery process as usually around 3 days, but it often varies by about 2 days, and then connect that to customer expectations, refund policies, and staffing needs for support. The value of this framing is that it turns spread into a practical planning input rather than a statistic that sits beside the mean without changing decisions. When dispersion is described as predictability, the audience hears why it matters, not just that it exists. Quick validation checks help ensure that dispersion numbers make sense, and one of the simplest checks is comparing them to the minimum and maximum values you observe. If SD is larger than the entire plausible range suggested by min and max, something is off, such as a type conversion issue, a unit mismatch, or a calculation that included invalid values. If the mean plus several SD suggests negative time or negative cost when the metric cannot be negative, that is another hint that either outliers or data defects are distorting the scale. This does not require deep math, only the habit of asking whether the spread aligns with the observed boundaries and with the real-world constraints of the process. When min and max checks are paired with a small sample review of extreme cases, dispersion becomes both interpretable and trustworthy. A spread story you can retell is a powerful way to summarize the concept because it ties the math to operational reality in a memorable sequence. The story begins with 2 groups that share the same average, then reveals that one group is predictable while the other is volatile, and the difference shows up in customer experience, operational escalations, and planning failures. It then connects volatility to causes, such as inconsistent handoffs, uneven demand, data collection gaps, or rare disruption events, making it clear that spread is not mysterious but often rooted in observable process conditions. Finally, it ends with the decision implication, which is that reducing spread can be as valuable as improving the mean, because predictability reduces risk and improves trust. When you can narrate that story cleanly, variance and SD stop being formulas and become part of how you reason about stability. The conclusion of episode 34 assigns a straightforward practice. Pick one dataset you work with, or one you can imagine clearly, and describe its spread in plain language alongside its center. The dataset could be delivery times, ticket resolution times, transaction amounts, or any measure where predictability matters, because those contexts make dispersion feel immediately relevant. The goal is to state what the average suggests, what the spread reveals about consistency, and what outliers or skew might be doing to the interpretation, all without hiding behind jargon. When you can explain spread as operational stability, you are prepared for the exam's reasoning questions and for real stakeholder conversations where the core concern is risk, not math. One careful spread description today builds a habit that keeps analysis honest and makes recommendations more credible tomorrow. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.